you. Morning, everybody. I'm going to talk about lattice structures, so metamaterials, and in particular, how to use a theory that is called percolation theory from physics to design new lattices with improved mechanical performance. So why metamaterials? Because over the past few years, they've been used quite a lot for energy absorption in particular, thanks to their good capabilities and also thanks to their lightweight properties, which is really important, like for if you use these for protective structures like bike helmets or whatever structure you want. There's two types of metamaterials. The first one on top here, it's a surface-based metamaterial. It's called usually TPMS, triply periodic minimal surface-based. And the second one is based on beams, interconnected beams. And this is a beam lattice. This is what we're going to talk about today. We've been working on this for a few time now, and we have developed our own framework. So we can start by defining the type of metamaterial we want to use. So either a stochastic one based on the Voronoi lattice, so a random lattice with beams placed randomly and connected randomly. And also there's the possibility to use a periodic lattice with a defined unit cell. You just need to define what unit cell you want to use, and then the framework will provide you with 4 different models. The first model is a CAD model, 3D model, and then 3 FEM models. One is based on beam elements, like the one you see here. One is based on 3D elements. They're all tetrahedral elements. And another one is a hybrid model, like this one here, where you have beam elements, but also a few unit cells, usually one, with 3D elements. And this is the best one because it's fast. It's a bunch of beam elements. And you can also get local stress and strains where you have the 3D elements. The hard part here is to connect the 3D elements to the 1D elements, but it's OK. And then the framework also runs the simulations for you. And you will get usually this type of response. This is the stress strain curve. So at the beginning, you have an elastic part. Then you have the plateau part, where the stress is at a plateau level, so just constant. And then after a certain strain, called densification strain, you'll have that the response picks up again. And usually, depending on the material, you can also have a peak before densification. We will call this peak stress. And we don't want this to happen because if you have a peak stress, like this guy here in the dashed green line, you will break your metamaterial before it can work as an absorber. So we don't want this peak here. This is the big point of this presentation. So I wanted to use this framework to study percolation, or to study something inspired by percolation and these metamaterials. So we can take a step back and see what percolation is. To understand what this is, we can start with the grid. This is not a metamaterial now. It's just a grid where we have white cells, there is no material. Where you will see black cells, there will be material inside the cell. Now we assign a probability P that a cell has material to each cell. And then through independent Bernoulli trials, we will assign materials. Bernoulli trials are consist basically on sampling a number from a uniform distribution. And then if that number is smaller than the probability P, we will put material. Otherwise, we just skip the cell. We go on with the next cell. So when you do so with the probability P 10%, you will see a bunch of black points. This is the material in our cell, in our grid. But there's no way that you can span the system from top to bottom, right? There is no continuous way that you can connect the top and the bottom face. But you can increase the probability to 20%, 30%, 40%, 50%, and 60%. And again, you won't see any path spanning the system from top to bottom. But now, when you increase the probability above 60%, this critical probability depends on the system. In this case, for a grid, is around 60%. You will get this light blue cluster. This is called percolation cluster. This allows you to span the system from top to bottom because there's a path. this one, that allows you to connect the top and bottom face. When this happens in systems, there's always a change of phase, and the properties, in this case, the mechanical properties of the system, will change drastically, and this is called percolation. So I wanted to use this to design new lattices to understand how this probability P affects the mechanical performance of the lattices. So instead of creating material, we will remove material from the lattice. So we will start from a fully connected lattice. This is a 2D example that's easier to see. So imagine these dashed lines are now solid lines. We have the full lattice. We assign a probability P to each beam, and that is an absence probability. So we sample a number from a uniform distribution for each beam. If the number is smaller than the probability P we assign to the beam, then we remove the beam, okay? And we'll end up with a full lattice without some beams. We've already verified that the relative density of the lattice, so basically the weight of the lattice, linearly depends on the absence probability. So when you remove beams, of course, you remove in a linear way also weight, which is what we want. We want to make these structures lighter. And we ran numerical simulations using the framework that I showed you before. So this is the first kind of model you can have. It's fully based on 1D beam elements. It's Timoshenko beam elements. The material we use, it's a polymeric material because this is meant for like bike helmets. So we don't use metals here. It's too heavy. In this case, we use PA12. There's a lot of material models you can use. We just use a linear viscoelastic isotropic model because for metamaterials, the most interesting thing is the geometry, not really the material model. And we had two loading conditions applied through these rigid plates. The bottom one is fixed. The top one moves, compresses the metamaterial, and it moves at 3.5 meters per second in one simulation, at 35 meters per second in another simulation. So we'll have these two loading conditions, but the metamaterial is this guy here. And you can see there's a few beams removed from the lattice. Now, if you study what happens when you remove beams starting from 0% probability, which is like the full lattice, up to 50% probability, which is the lighter color, you will see that the plateau part of the stress strain curve gets reduced. Of course, the absorbed energy, that is the area under the curve, gets reduced, of course. Densification stays there. And if you identify the peak stress as the maximum stress that you have before densification, in this case, it's just the beginning of densification, there's not really a peak stress. You can also see that the peak stress gets reduced. Now, if you want to create trend lines, you will see that the absorbed energy depends linearly on the absence probability P. You will see that the plateau stress depends linearly on the absence probability P, but you will see that the peak stress instead is described by a power law. And this is interesting because if you use very small absence probability, you will decrease the peak stress faster than energy absorption. And we don't want peak stresses here. So this is the case for 3.5 meters per second. When you go to 35 meters per second, you will see that there's a few peaks popping up here. This is what also experimentally we see, even though usually they are larger, much larger. And again, if you draw some trend lines, you will see that the absorbed energy is linear in terms of P. Plateau stress is linear in terms of P. And again, peak stress is a power law. So we still confirm the results also at higher velocity. But this is 1D simulations. And we know that for metamaterials, contacts are an issue usually. And with 1D simulations, they are even more an issue. So we try to verify the results with the 3D simulation. This is the 3D model that you can get from the framework we developed. It starts from a CAD model, and then we fill with tetrahedral elements. We cannot use hexahedral elements in this case because we cannot follow the geometry with hexahedral elements. So we need to use tetrahedral elements. Anyway, we do sensitivity analysis and everything, and again, the material is the same. Loading conditions, again, at 3.5 meters per second and 35 meters per second. So same loading conditions we saw before. Now I'll show you the results for two absence probabilities, 1% and 20%. When we use 1%, which is this lattice here, we see that the beams are almost all there. So this is basically the full lattice. When we will see 20%, we will see that a few more beams are removed. But just to show you what happens when you remove beams, you can see that as we travel from 1% to 50%, the lattice starts to lose its connectivity. And here it resembles a Voronoi lattice, like a random lattice, but it's still based on a unicell. I didn't mention this, but all these lattices are based on a Kelvin unicell. So this is not a random lattice. It's a Kelvin lattice without 50% of the beams. Well, when you look at the 1% absence probability with impact velocity 3.5%, you will see that the 3D and 1D simulations are a bit different. Finally, we get this big stress in the 3D simulation that we couldn't capture with the 1D simulation. This was due to contact issues. But yeah, the rest of the curve is pretty much the same. When we look at the higher velocity, 35 meters per second, you will see that we get two peaks now in the 3D simulation. We also have something in the 1D simulation, this peak here and this peak here before the plateau part. But again, the peak stresses now are a bit, or a lot larger. And when you go to absence probability 20%, you will see again that we get a bit of a peak here in the 3D simulation. And we also get another peak if we go faster with the top plate, if we increase the strain rate. Which means we need to do everything from scratch, because the 3D simulations can now capture the peak stress, while the 1D simulations cannot capture the peak stress. So we did a few simulations. Actually, we simulated all these lattices here. Each simulation takes an hour, so we couldn't simulate like an infinite number of lattices. 6 was okay for us. And if you look at the results for those lattices subjected to a velocity of 3.5 meters per second, now you will see that we can reduce the peak stress by a lot. The absorbed energy gets reduced again, and the plateau stress, it's very similar, but it still gets reduced. And if you look at the absorbed energy now, you can see that it's a linear trend with respect to P. We also tried to fit to an exponential curve, but the residual was too large. So that is a linear trend. And if you look at the peak stress, now it's a power law again. So before with the 1D simulations, we already saw it was a power law, but we didn't have a real peak stress. Now we have it. And we can reduce it through a power law. And now if you look at the percentage reduction of peak stress, red line, and absorbed energy, blue line, of a lattice with a probability P compared to the full lattice, you will see that the peak stress gets reduced faster than the absorbed energy. And the optimal point for this lattice is this probability P, which is 26.9%. At this probability, you have the maximum difference between the two curves. So here, you have reduced the peak stress by 70%. It's not there, basically. And you have reduced absorbed energy by 37%, which is okay. And if you look at the simulations, now with 35 meters per second, so 10 times faster, again, you see there's two peaks, and both peaks gets reduced. And if you look now at the yellow curve, you will see that basically there is this light peak here, but it's basically plateau and then densification. So we got rid of the peak stress. And again, like same plots, absorbed energy is linear with respect to P, and peak stress is a power law. And again, if you look at the difference between peak stress and absorbed energy, you will see that the optimal point for this lattice is now 29.6%. Here we have reduced the peak stress by 68% and the absorbed energy by, again, 37%. This is specific to Kelvin lattices. We've tried this with a few other unicells like octet or other ones. And always this optimal point P is between 25 and 30%. So that is the optimal point if you want to reduce completely peak stress while keeping enough absorbed energy. You could also try to design a new lattice if you want to. If this is your target absorbed energy, you can also design a new lattice without removing beams, but then you will get a peak stress. So this method is really useful for getting a desired absorbed energy without peak stresses. That is what this is meant for. So we have presented a numerical framework. You can start from any lattice that you want, random or periodic lattice with unit cells, and you can get CAD models, FEM models, and do simulations. We use this framework to understand how percolation or percolation-inspired theories can be used for lattices. And we saw that we can optimize mass, basically get a lighter structure, while improving the mechanical response in terms of peak stresses. We can reduce the peak stresses and avoid to break the material before it can work as an absorber. Of course, you cannot go past the threshold. We saw there's a critical threshold for percolation, after which we lose connectivity. There is no connection between top and bottom, right? So of course, we don't want to go past 50%. Otherwise, the metamaterial is not connected anymore and it cannot work. And we also saw that in this case in these type of structures, we need to use 3D models, not 1D models. Otherwise, we lose a lot of information. We're now running, it's not here, but we're running experiments now. This is in collaboration with NTNU, University in Trondheim, Norway. They're running experiments, so we will soon verify all numerical models and get ready for submission, hopefully. Thank you.